and that forms 8 iron sulfides, FeS. So if 4.2 moles of S8 reacts, what mass of FeS is produced? Here in this problem, if I call S8 like chemical A, and I call FeS chemical B, what we're starting with is a number of moles of this chemical A. That's this right here. We're starting with moles of chemical A, and I'm trying to figure out what mass of iron sulfide is produced. That's a mass in grams of this other chemical, chemical B, like over there. So I've got to get from moles of chemical A into grams of chemical B. And the fastest way to do that is to convert from moles of A into moles of B, and then convert from moles of B into grams of B. That's how that concept map can help you kind of figure out where you got to go. So anyway, you can start by writing the quantity that you know. You got like 4.2 moles of S8. You don't write A and B. That's just a generic like chemical A and chemical B. So you have 4.2 moles of S8. What we can do is convert that into a number of moles of chemical B, and you use a mole ratio. So this mole ratio, whatever the unit is in the denominator, like moles of S8, that goes in the denominator, and you can't convert straight into a mass of iron sulfide, but you can convert into moles, like moles of FeS. That's this first conversion. You're going from moles of chemical A into moles of chemical B. And the numbers that go here are whatever the mole ratio is in the balanced chemical equation. This equation is already balanced. So in the equation, there's one S8, but there are 8 iron sulfides. Those numbers come from the coefficients in the balanced chemical equation. Or in other words, for every 1 mole of S8, we're going to get 8 moles of FeS. So if you start with 4.2 moles of S8, you're going to get 8 times more moles than that of iron sulfide. So at that part, you have converted from moles of S8 into moles of FeS. But the problem is to calculate how many grams is produced. So we got to convert from moles to grams, and you convert from moles to grams using the formula mass. So every 1 mole of FeS, I don't know, I got to find it. Got to get me a periodic table. Let's see. WSD. I had one up before, and then I got rid of it, I guess. I get the same digits as what's on your table. Okay, so iron's 55.85. So you got to figure out the formula mass. It's iron and sulfur. There's 1 iron and 1 sulfur. Iron has a mass of 55.85. Sulfur is 32.07. So you just, I mean, you just add these up because you don't really have to multiply. That's kind of dumb. 87.92 grams per mole. Yeah. So the mass of iron sulfide is 87.92 grams. Notice I write what chemical it is when you do the conversion, because that allows you to keep track of like what chemical you're working with and which one you're on. So this is straight up stoichiometry. This is as stoichiometry gets. So in other words, if you start with 4.2 moles of sulfur as S8, how much mass of iron sulfide do you get? The math is 4.2 times 8 times 87.92. 4.2 times 8 times 87.92. So it's like, well, it comes out to be 2954.112. But we only have two significant figures. This is actually kind of a fun one with significant figures because the 4.2 has only two significant figures, we got to round this to two significant figures, but it's not 2,900. It would have to be 3,000, but you have to express 3,000 with two significant figures. And you can do that one of two ways. You can write 3,000 and underline that zero, or you could write it in scientific notation as 3.0 times 10 to the third grams, but you get about 3,000 grams, give or take 100 grams. So this first step is a mole ratio. That's this first step here, going from moles of one to moles of the other. And the second one is the formula mass, going from moles to grams. So really just combining the ideas and things from, well, a lot of the course. If instead 13 moles of iron react, kind of start over, and we're trying to figure out the mass of iron sulfide, it's the same deal, but we're beginning with a different chemical. In the reaction, for every 8 irons, you get 8 iron sulfides. I'll write mole because 8 mole iron, you get 8 mole iron sulfide. Because in the equation, the coefficients in front of each iron and iron sulfide, they're both 8. And it's the same formula mass. 1 mole of iron sulfide is 87.92 grams. These units, moles cancel out, moles of iron sulfide cancel out, and leaves you with grams of iron sulfide. So now we got, it's going to be something different. So 13 moles of iron is more moles than the number of moles of S8, but now the mole ratio is different, 8 and 8. So despite the fact that you have a greater starting quantity of iron, for every one reaction, it takes 8 irons to make the reaction go, but you only need one S8 to make the reaction go. So 13 times 87.92, it's 1,142.96, but we only want two significant figures, so 1,100 grams is good. So another way to look at the problem is all the time there's two parts to the unit. Like you had moles of S8, and we're trying to go to a mass of FES. So you have to change from both moles to grams, moles to a mass, and change from one chemical to the other. If you're trying to relate two different chemicals, you're going to use a mole ratio. Like if you're relating chemical A and chemical B, you must do it with a mole ratio. There's no choice but to have the mole ratio. So this is the mole ratio, and this is the formula mass. So this is like, that's step one, the mole ratio, and this is a formula mass. You could do the same thing for relative masses and quantities of anything. It's useful application in, calculating quantities for things for manufacturing, figuring out ratios of things for cooking and whatnot. If you're like, you want to scale a recipe up to go from a certain serving size to another serving size, you can scale recipes up and down using the same types of ratios of masses and volumes and relative quantities. All right, questions about that? Okay, so the second example, it's like on the back, same kind of deal. There's a chemical equation here, and it's a decomposition reaction. Let me grab that mole map thing and stick it on here again. Get this over. So it says if 5.5 moles of NaClO3 react, how many molecules of oxygen are produced? So we're starting out with moles of one chemical. If we call this chemical A and oxygen, we call it chemical B. We're beginning with number of moles of chemical A. That's right here. And I'm trying to figure out how many molecules of oxygen. So the first thing you got to do is convert from moles of one chemical into moles of the other. And then you can convert into number of individual molecules. You can't go from moles of one to molecules of the other directly, but we can convert from moles of one to moles of the other, and then from moles to molecules. So all the time, whatever value you begin with, like 5.50 moles NaClO3, you write both of those things, both the unit for the quantity and which chemical it is. And because we need to convert from one chemical to the other, and we're already in moles, you can straight up use a mole ratio first. And in this balanced chemical equation, for every 2 NaClO3, so 2 mole NaClO3, we get 3 moles of oxygen, 3 mole of O2. So if you begin with a quantity in moles, the first thing you can use is a mole ratio. That's how I went from like moles of one chemical to moles of the other. And then I want to convert into molecules. Every mole of anything has 6.02 times 10 to the 23rd, like particles, but in this case, they're individual molecules. They could be atoms, they could be molecules, could be formula units. So that comes out to be 4.9665 times 10 to the 24th. But we only have 3 significant figures in the 5.5. Usually you have as many significant figures in the answer as whichever the values you start with has for significant figures. So we want only 3 here, 4.97 times 10 to the 24th. So what that means is if you take NaClO3 and you do decomposition by heating it, when you heat this up, it'll decompose into sodium chloride and oxygen. And when you take 5.5 moles of that chemical, you should expect that you'd end up with 4.97 times 10 to the 24th molecules of oxygen. At STP, how many liters is that? So that's a different path on this concept map. We started with moles of chemical A, so I'll put this in green. We change that into moles of chemical B, the oxygen, and then we got to change it into a volume in liters. So you're going from moles of chemical A into moles of chemical B, and then you convert it into liters. So the first step is exactly the same, 5.50 moles NaClO3 but if you want to figure out how many liters of oxygen that is, once you're in moles of oxygen, you can convert to liters using Avogadro's law. Every mole of oxygen has a volume of 22.4 liters. That's the new thing from yesterday, converting from moles to liters. So let's see, 5.5 times 3 divided by 2 times 22.4. Well, it says 184.8, but we only want to have 3 significant figures, so 185 liters. That's the volume of oxygen. There's another thing that people write. It's kind of like a little shortcut. Is because the first 2 steps are identical. You start with a quantity of whatever chemical you know, and you use a mole ratio to do the conversion. What I wrote at the beginning, the 5.5 moles NaCl3, and this conversion factor, they're exactly the same. So the only thing that's different is the last conversion factor. So you'll see this written a lot, and it's like a little bit of a shortcut, is because the beginning is exactly the same, you can also just, people write like a little arrow and then write 22.4 liters and 1 mole. And really, it's kind of another path. So instead of rewriting all this out, if you just like, you know, draw an arrow and write 22.4 liters over 1 mole, then the math is 5.5 times 3 divided by 2, and then times 22.4. You're really doing the same thing. You just don't rewrite it all. There are other quantities for oxygen you could have. Like if you want to know individual number of atoms, you could convert from moles to atoms and then atoms to molecules and kind of have that step up here. So that can save a little bit of writing, and you'll see that in different kinds of references. I know, like if you watch stoichiometry in Khan Academy, they show the exact same thing. That's what a lot of people do. So anyways, the last example, how many grams of sodium chloride would be produced if we start with 160 grams of NaClO3? Let me get a fresh map on there. I know it's all the same map on your paper, but in this case, I'm trying to go from the mass of one thing, like the mass of NaClO3, into the mass of another thing, NaCl. So on this map, I'm going from the grams of one chemical to grams of another. There's going to be 3 conversion factors. You got to convert from grams to moles, and then from moles to moles, and then from moles to grams. There's no other way. There's no other way. There's no shortcut. There's no alternative method. It's what every chemist does. If you got 160 grams of NaClO3, how many grams of sodium chloride do you get? 100% of the time, you convert from grams to moles, moles to moles, moles to grams. So 160 grams NaClO3. First thing you got to figure out is what's the formula mass for that NaClO3. I'll tell you what, I'm gonna make this neater. So, because you got a bunch of space on your paper. Let's see. Let me copy this down. That didn't do what I wanted it to do, but it's all right. Hey, what's going on? You got dank memes. Nothing but trouble, huh? Yep. All right. Later. See ya. Let's see. Let me fix this up. Grams of one to grams of the other. We got to go this way, this way, this way. Okay. So I don't know. Let's see. 160 grams. Mr. Harris is a huge troublemaker. Formula mass. So we got 1 sodium, 1 chlorine, and 3 oxygens. So sodium is what? 22.99. Chlorine 35.45. And oxygen 16.00. So that's 35.45. Let's see, that's going to be 48. 106.44. So to convert from grams of NaClO3 into mass, or into moles, it's 106.44 grams per mole. So that got me from grams of NaClO3 into moles of NaClO3. Then I got to convert into moles of NaCl. So in the equation, for every 2 NaClO3s, I get 2 NaCls. For every 2, all right, mole, 2 mole NaClO3, there's 2 moles NaCl. And then we got to convert from moles into grams. So the last step is that every 1 mole of NaCl has a particular mass. And it turns out there's kind of like another little shortcut here. Because I've already kind of done a bunch of math to calculate the formula mass for NaClO3, it turns out that however much this is, really just the mass of sodium plus the mass of chlorine, 22.99 plus 35.45, that is the total mass for sodium chloride. So let's see, that's another, so it'd be 58.44 grams. Kind of ended up writing on top that. It's kind of a mess. So we got to go 160 divided by 106.44. Here, because you're going to multiply and divide by 2, you don't really have to type anything, but then times 58.44. 87, let's see. $87.85. Oh yeah, that's wrong. All right, 87.84667, whatever. But we've got two significant figures. This 160 grams only has 2 significant figures because the 0 at the end of larger values are not significant. So we get 88 grams of NaCl. So that's how it goes. In this case, we went from grams of one thing into grams of another. So you can go from any quantity into another using that concept map. It's usually just as simple as if you don't have a quantity that's in moles, you first convert it into moles. And then to relate one chemical to another, you use a mole ratio. And then once the mole ratio is done, then you can use formula mass, Avogadro's number, Avogadro's law to convert it into some other kind of quantity. All right, so the other paper in the upper right-hand corner, it says like mole map conversion quick check. So there's some equations you need to make sure they're balanced correctly because the other ones were balanced correctly already. There's 5 of them there. Take some time right now and see what you can get for figuring those out. Let's see. The only thing you really need is a periodic table and calculator. Because unless, of course, you had a written description of the chemical and you had to like use an ion chart or whatever. So what Mr. Harris have? Was it like a picture of me? Or was it like a meme? No? I'll shake him down later.